This video is on section 5.5 in geometry. We're going to talk about more inequalities in triangles. In fact, we're going to finish the chapter on triangles with this lesson. So the first thing that I want to talk about in triangles is how the sides are related to each other. We already know that the longest side is opposite the largest angle and vice versa. The shortest side is opposite the smallest angle. But how, if we just ignore the angles, how are the sides themselves related in a triangle? What do we know has to be true about the sides of a triangle? Let me put it that way. So I've written the triangle inequality theorem on the board behind me, which says the sum of the lengths of any two sides of a triangle must be greater than the third side. You might think, why would that be the case? So I want to show you with an illustration. I have some different size rulers here. I have 1, 2, 3, 4 different rulers, and I want to make some triangles out of them. So let's say this is my one side of my triangle here. I'll pick this long one. If I want to make a triangle out of two of the other ones, I'll use these two. I can put one on this end, the other on this end. Will it make a triangle? Will they meet? And yes, they will. This makes a triangle. No problem. If I add up the length of this ruler and the length of this ruler, it will be longer than this, and that's why they come together like this and form a triangle. I hope you can see this. I hope I can even hold it. Anyway, there we go, and form a triangle there. Better with the black background. Let me trade one of this. Let me trade this ruler for the one I just tossed away. So I'm going to try the same thing. I want to make a triangle again. I have this ruler, this ruler, this ruler. Let me make a triangle. Now, so I'll put these on the two ends, and I will go to make a triangle. There we go. Go to make a triangle. And it doesn't work. All I've got is a line, a flat surface, because they don't meet. They're too short. So I can't, they will never make a triangle. These two, if I added these two sides together, are not longer than this side. Even if they're exactly the same length, they will still just touch on top of the ruler and still not form a triangle. They don't have to be a lot bigger, just a little bit bigger. You could still make a crazy thin triangle, which I'm trying to show here, but they have to be bigger. They can't be equal. They can't be smaller. This is why. So with that theorem in mind, could I or you make a triangle out of 3 sticks? One is 9 centimeters long, the other is 6 centimeters, and the other is 5 centimeters. Would they form a triangle? And is 9 plus 6 greater than 5? It is. Is 9 plus 5 greater than 6? Yes. And is 5 plus 6 greater than 9? Yes. So this one would form a triangle. Let's try the same exercise. I traded out my 5 centimeter stick for a 2 centimeter stick. So now I have 9 centimeters, 6 centimeters, and 2 centimeters. Would that form a triangle? And 6 plus 2 is not greater than 9. So if this was my 9 centimeter long side, my 2 inch and my 6 centimeters would just lay flat, wouldn't form a triangle. What about 9, 5, and 4? Would that form a triangle? Again, the 5 and the 4 would be exactly equal to 9, so it would just lay right flat on top. It's got to be a little bit bigger to come up off the top and form a triangle. So this one would not work either. Okay, this is a common type of question that you are asked regarding this triangle inequality theorem. I have 2 sticks. I want to make a triangle. One of them is 4.7 centimeters long and the other is 6.8 centimeters long. What range of lengths for my third side would be able to form a triangle? So you could set up equations using the triangle inequality theorem. That third side we'll call x, and we know that 4.7 plus 6.8 would have to be greater than x. Also, 4.7 plus x would have to be greater than 6.8, etc. I'll write them down. Come right back. You can set up these three inequality equations, solve for x in all three, and then come up with the results. But I would like to show you a much simpler way to do this without having to go through that process, which would be kind of tedious. Let me go ahead and walk through this process, and then I'm going to show you an easier way to do it. So I'm going to add these two together. That gives me 11.5. I'm going to subtract 4.7 from 6.8. That'll give me 2.1. And I'm going to subtract 6.8 from 4.7, which will give me negative 2.1. Okay, here is the result. My third side has to be smaller than 11.5 centimeters, and it has to be greater than 2.1 or negative 2.1. I can throw away the negative 2.1. That's extraneous. We know that. It's got to be greater than 2.1. So I can write my results, and I want you to write your results like this. Our third side would have to be somewhere between 2.1 centimeters and 11.5 centimeters. That's the way that you would do it. But let me show you how we came up with those numbers. If you take the other two sides and you find the difference between them, you subtract one from the other, that gives you this number. If you take the other two sides and add them together, that gives you this number. So that's all you have to do to find the range of possible third sides to make a triangle with these two. So subtract them, that'll be here on the left. Your x has to be bigger than the difference, and it has to be less than the sum so that that relationship will work. I have two sides of a triangle. I don't know what the units are. I'm not going to worry about that. But one has a length of 4. One has a length of 9. What is the range for the third side that will actually form a triangle? Knowing that the sum of any two sides has to be greater than the third side. So to answer this question, you just put the third side has to be greater than, and you subtract 9 minus 4, which is 5. And it has to be less than, add 9 plus 4 is 13. It has to be somewhere between 5 and 13. That's because 5 plus 4 would equal 9, so it's got to be a little bit bigger than 5, so that those two will be greater than 9. And 4 plus 9 is 13, so it's got to be a little bit less than 13, so that the sum of these two sides would be able to form. That's how it works. Another application of this theorem is coming up with really efficient work triangles. If you're designing a kitchen, you want to set things up so that there are distances between places that you have to go to often, like the stove or the refrigerator or the sink, are easy to get to. And if you can have a nice working triangle, that makes your time much more efficient and the kitchen a lot less frustrating to work in. So you come up with a few plans. These numbers would represent distances between these, like maybe between the stove and the refrigerator, or the refrigerator and the sink, or the stove and the sink. Which one of these would form a really good work triangle for you? So if we look at this first group, 5, 7, and 6, all three sides fit the triangle inequality theorem well. 12 is greater than 6, 13 is greater than 5, 11 is greater than 7. So that looks like it would work. If we look at these, we realize 4 plus 6 equals 10. That won't even form a triangle. That will just form a straight line. So now I have everything in a straight line. and I'm just walking back and forth, back and forth. Yeah. I don't like that one. This top one would work much better. Okay, another inequality theorem is more comparing between two different triangles. The triangle inequality, or the one that we just did with the sides, is in one triangle. Hinge theorem deals with two. And the best way to picture this for me is to think of a door. Okay, a door is just like a flat line right here, but if I open the door like this, the size of my door doesn't change. The size of the threshold of the door or the door frame doesn't change. But as I open the door wider and wider and wider, what happens to this third side right here? The greater the door, you open the door, right? The greater this angle is here, the greater that side, that gap is that you've created. So here's the same size door. I've opened it a little further. So this angle here is greater than that angle. If that's the case, then this side is greater than that side. So if you're dealing with two triangles and you have two congruent sides, think of them as similar to your door frame and the door itself, then compare this included angle. Whichever included angle is larger, then you know the side across from it, it's going to be longer than the side in that. So there's a comparison here between the two triangles. That's the hinge theorem. Doors work on hinges. And if you can think of that relationship, then when you get a problem, it can make sense to you and you can figure it out, even if you don't memorize the actual theorem, which is in your book. Write down in your notebooks, but this is what it means. You open the door wider, the wider you open the door, the greater this gap here. Narrower the opening of the door, the shorter this gap. So I can compare two different doors, same size doors, but they may not be opened the same amount. That's the hinge theorem. The converse of the hinge theorem is exactly the same, just flipped. So let's say I don't know anything about these angles, but I do know the size of the opening. And I've realized this opening is a little shorter, a little smaller than this opening. What does that tell me about the angle opposite it? This angle would have to be smaller than that angle. So the converse also works. This is an example of a hinge theorem problem. The answer is just terribly obvious, but that's okay. It still shows you how the hinge theorem works. I have two triangles, triangle ABC and triangle DEF. Notice they have two congruent sides. AC is congruent to DF, BC is congruent to ED. The angles, included angles, are not the same. This angle C is 40 degrees, angle D is 120 degrees. Based on all that information, how are AB and EF related? And you might even look at them, hopefully, and think about it, because angle D is much larger than angle C, then the side across from angle E, which is EF, would have to be greater than the side across from angle C, which is AB. So AB is smaller or less than EF. I probably should have shown that they were segments. There we go. Now that's an application of the hinge theorem. Here's another application of the hinge theorem. I have this figure, two triangles inside of it. These two sides here, KN and LM, are marked congruent, and KL is marked 5 and NM is marked 7 in our diagram. I want to compare two angles. The angle KNL, which is this angle here, and measure MLN, which is this angle here. And I'm telling you the hinge theorem applies. The reason the hinge theorem applies is because both of those angles share the side in L here, which is congruent to itself. So its second side is congruent. I have two congruent sides, KN and NL, ML and NL. Okay, so how do the angles compare? I need to look at the sides across from it. NM is 7, KL is 5. This is the larger side, therefore it's across from the larger angle. So angle MLN would have to be greater than the measure of angle KNL. And this is an inequality. You're not looking for an exact number, you're just looking for a relationship. Here's another example or application of the hinge theorem. You may be asked to give a range of possible values. In this case, we want to know what's the range of possible values for x. What could x be? And this diagram would still be accurate. So look, notice I have my two corresponding sides, and I'm given the included angle. This angle is greater than that one. 100 is greater than 70. That means 3x minus 1 has to be greater than 5 minus x. So I will set that up like an equation or an inequality. 3x minus 1 is greater than 5 minus x, and then I'm going to solve for x. So I'll add x here and add 1 here. I get 4x is greater than 6, so x is greater than 3 over 2, or 1.5. So I know my x can be bigger than 1.5, but I don't know what the upper limit is. It can't go on to infinity. There must be a limit for this to still be true. And the limit is the fact that for this to be a triangle, this side has got to be greater than 0. Otherwise, it's not a triangle. So my second equation is 5 minus x has to be greater than 0. Which means when I add x to both sides, that x will be less than 5. So my x will be greater than 1.5 and less than 5. That's the range of possible values for my x for this diagram to still be accurate. Okay, let's look at a few practice problems to see how this applies. This is kind of a review of what we've done in this video so far. With this hinge theorem, how are UV and VW, the lengths of UV and the lengths of VW, how are they related using the hinge theorem? Hopefully you saw UV is greater than VW because the angle across from it is greater than the angle across from VW. And remember, they share this corresponding side of Vx, so that's why the two sides are congruent. Another one, I have these two triangles using the hinge theorem. Can you tell me the relationship between the measure of angle BCA and the measure of angle DCA? Notice how everything's marked. What do you think? BCA has to be greater because the side across from it is longer than the side across from DCA. All right, here's another practice problem for finding the range of possible values for x. I would like you to pause the video, look at the diagram, see if you can do it, restart the video, and see how you did. Hopefully, using the hinge theorem, you realized that 2x plus 3 is greater than 3x minus 2, and so you saw that x has to be less than 5. You also realized that 3x minus 2 has to be greater than 0, which means x has to be greater than 2/3. So x is less than 5 and greater than 2/3. How did you do? Okay, that's the end of this section on triangles. In fact, it's the end of chapter 5. So get that work done, study hard, review if you need to. And next time we get together, we will be talking about quadrilaterals in chapter 6. So I'll see you then.